The way that music is represented inside a computer is crucial in determining how that musical data can be used. For example, in the last video I demonstrated my own program, Example Crafter, and showed how it represented music as an image, a bitmap file, and as a PostScript file, instructions on how to engrave the music. The image file is static. It can't be changed. The PostScript file, on the other hand, can be easily transformed. For example, the musical symbols in the Sonata music font can be replaced by symbols from another font, say a jazz music font. Even though the PostScript file produced better results, the bitmap file also had its advantages. It could be displayed using standard computer software, and it could be printed on standard computer printers of the day. When I was writing my software in the 1980s, printers capable of printing PostScript files were more expensive than standard printers because PostScript was a proprietary product of the Adobe Corporation. Printers that used it had to pay a licensing fee to Adobe. There is no best way to represent music inside a computer. Each method has its own advantages and disadvantages. As a music scholar, I'm concerned about my own research, and I'm concerned about which musical representation suits my own needs. In 1988, I went to Lancaster, England to read a paper about a computer representation system I'd devised. The problem I hoped to solve was how to produce a library of musical scores that could be stored in and manipulated by computers. Walter Hewlett was already working on the same problem at the Center for Computer Assisted Research in the Humanities in California, and my representation was inspired by his work. Hewlett created an encoding specification that included all of the information necessary to reproduce the original notation. For example, there might be a specification for an eighth note that included a pitch, a voice number, a stem direction, a flag or beam style, and so on. The problem with this kind of definition was that it would never produce a closed system that could describe every possible musical event. As soon as you have everything defined, a new novel situation arises that requires a new definition. That kind of system seemed impractical to me. What I wanted was something simple, so I could just get on with my research. It seemed to me that what most people were interested in was pitch and rhythm information. These needed to be represented inside the computer as codes that could be searched and transformed as needed. All of the other musical information could be saved as a scanned image so that people could consult it if they needed to. I didn't see any reason why all that extra information needed to be machine readable, since my research was primarily concerned with pitch and rhythm. I linked the scanned image to the pitch rhythm codes by location on the image, by coordinates. For example, the first code in the pitch rhythm codes would be linked to the first note in the scanned score. The user would only see the score and would be able to search for motives and rhythmic patterns and patterns of pitch via the pitch rhythm codes. The user would never need to see those codes themselves because the computer program accessed them invisibly via the locations of the notes on the screen. Here's a prototype for the program. In this example, I scanned a piece by Sterling Casaubon that existed only in manuscript. I chose this piece for the prototype because I wanted to demonstrate that, since the notation was a scanned image, the actual notation of the original didn't matter. It could be professionally typeset or handwritten, or it could even be some sort of unique idiosyncratic graphic notation. The demo included mundane but useful features like the addition of critical notes, or the ability to write marginalia on top of the notation in an invisible layer. The user could select notes on the screen and search. It was possible to search for motives that included both pitch and rhythm, or just pitch, or just rhythm. The user could select notes on the screen and extract them as an excerpt that could be imported into a simple music notation program, so that they could be used as musical examples. The user could also do various types of statistical analyses, like finding out how many of each melodic interval occurred in the piece. Here's an example of the actual pitch and rhythm information. It was just a string of characters that represented pitch, octave, and rhythmic value. After I gave my paper at the conference, I got a few polite comments, and that was about it. Nobody seemed particularly interested in this type of computer representation. What they were interested in was the type of representation that was proposed by David Huron. Huron realized that not everybody needed to represent the same kinds of things, so he proposed a flexible representation. At its most simple, his humdrum representation might consist of a single column of pitch rhythm codes. A second column, a second voice, could be added to the first. In order to sync the voices up, Huron added placeholder dots in each voice in places where one voice moved rhythmically and the other didn't. Other columns could be added to this array of pitch and rhythm. For example, a column of lyrics could be added. Words would appear in a separate column in the locations where the syllables were sung, and dots would be used on notes where no words appeared in the score. Any kind of data could be added in additional columns. Dynamics, articulations, orchestration, playing techniques, figured bass. All of this information was synced up using the placeholder dots. The brilliant thing about this representation was that it could literally include anything, but it didn't have to include anything specific. Having all of this information in a computer-readable form allows music theorists to do a kind of musical data mining. This data mining usually takes the form of what is known as corpus studies. We have a problem with sample size in music theory. We will pontificate about what is typical of a certain musical style based on only a few cherry-picked examples. For example, Rameau and other theorists after him saw root movement by descending perfect fifth as the basis of chord progression. Rameau based his theory primarily on the music of his own place and time. It's a pretty small sample. Today we have several hundred more years of music history, and we now know that Rameau was wrong. At least he was wrong about root movement by perfect fifth being universal. But maybe he was correct about chord progressions in the 18th century. I decided to test this proposition by analyzing a select body of 18th century music, Bach chorales. I found that Craig Sapp had encoded 69 of them using David Huron's humdrum system. Sapp added an extra column to the chorales, a Roman numeral analysis. This made my job much easier, since I could create a simple program that searched for the fifths based on the patterns in the Roman numerals, rather than analyzing the chords myself to find their roots before looking for the root movement. The program I created found instances of descending perfect fifths and ascending perfect fourths and tallied them. Then it generated some statistics. One of these statistics was the percentage of root movement by perfect fifth, which turned out to be 37%. This number was not the definitive answer I had hoped for. It's hard to believe that something that occurs only 37% of the time is the basis for harmonic progression in the 18th century, and yet I also found it hard to believe that Rameau was totally wrong. So I created some other programs that searched for additional patterns. Probably the most interesting of these additional searches provided data about cadence types in the chorales. Sapp had included fermatas in the data he encoded into the humdrum files, so finding the cadences in the chorales was as simple as searching for the fermatas. While the search showed that Bach used a wide variety of cadence types, he used the same kind of cadence to end the chorales almost all the time. Of the 69 chorales, 67 ended with authentic cadences. So while I can't say with certainty that all chord progressions in 18th century music are based on descending fifths, I can say that endings of Bach chorales are based on this kind of movement. For Bach, this was a very strong progression, and it was used to produce closure. I'm a big believer in these kinds of corpus studies, and it seems to me that we need computer-readable scores in order to make them practical. That doesn't mean, however, that computers are absolutely necessary. The earliest corpus study I know of was conducted by Daniel Jellensberger in the early 19th century. Jellensberger was interested in modulation, and he wanted to find out which keys we used the most frequently by composers and how long the music stayed in those keys. His conclusion was that the music he studied was in the tonic key in the major mode 57% of the time. It was in the dominant 11% of the time. It was in the minor version of the tonic key 5% of the time, and in the subdominant a little over 4.5% of the time. It was in a minor submediant at 4.4% of the time. All of the other keys occurred less than 4% of the time. Given that, it's interesting that two keys based on non-diatonic scale degrees were the next most prominent. A major flat 3 at 3.9%, and a major flat 6 at 3.3%. The least used key was the minor key at the tritone. In all of the 27,000 odd measures examined, it occurred in only 4 measures. A more recent study was done by my brother Scott on textures in Haydn trios. He analyzed textures in hundreds of trios by Haydn and his contemporaries. Tabulating the results by hand was a huge chore, and while it was possible, using computers would have sped up and simplified the process. While talking about music and mathematics, I would be remiss if I didn't mention the analysis of 12-tone music. Even before computers were available, music theorists were using numbers to analyze 12-tone music. The main reason for this is that 12-tone analysis is primarily concerned with the tracking of the transformations of a series of pitches. The 12-tone row is an ordering by the composer of the 12 chromatic pitches in such a fashion that it forms the basis of a piece. Some have likened the row to a scalar mode, while others describe it as a kind of proto-melody. A 12-tone row can easily be described by numbers. The first pitch can be assigned the number 0, and subsequent pitches can be assigned numbers based upon the number of half steps they are above the 0 pitch. Just such a numerical approach is found in Alan Fort's book, The Structure of Atonal Music. This book has become a standard text for 12-tone music. Fort has a rather complicated system. This is necessary because Fort deals not just with 12-tone rows, but also with smaller sets of pitches, 3, 4, 5, and 6-note groups. Fort has cataloged these sets of pitches in the back of his book and given each a numerical name, like 4Z29. People who use this method regularly have many of the names of these sets memorized and can dazzle non-Fortians by using these numerical names to describe the relationships amongst the sets of pitches. For my example today, I've chosen a known 12-tone work, and I won't strictly follow Fort's method. Still, the following demonstration should give you an idea of how numerical analysis works. I've started out by translating all of the pitches of the first 2 pages of the 5th movement of Anton Webern's second cantata into numbers. I have arbitrarily chosen the leftmost uppermost pitch as 0. Our task as analysts is to find the original row and each one of its transformations. We could start out with a simple search. The first 2 pitches are probably the start of the row, so if we search for instances of those first 2 pitches, we should find the beginnings of various statements of the row. What we find is not helpful. There's only one place where these 2 pitches happen consecutively. Perhaps we should search for all possible transpositions of these 2 pitches. Now, we have so many hits that it's impossible to tell what's going on. While it still seems likely to me that the row begins with a half step, so many half steps must be included further on in the row that finding them gives us no clue as to the start of a new row. This method of arbitrarily searching for patterns might not be the best way to analyze the piece. What we need is some kind of structure to the data. We need a representation that segments the data into meaningful, recognizable chunks. I suggest separating the data into lines that indicate which instruments or voice types perform the music. Then, let's arrange the numbers so that they represent temporal position, so that the pitches sounding simultaneously are vertically aligned. I'm also adding in bar lines to help me keep my place, and I'm spreading out the numbers so that each system in the score is on a different screen. The data now suggests larger patterns. For example, those first 2 pitches we searched for earlier are part of a 6-note group in the choir soprano. Maybe those are the first 6 notes of the row. We see other 6-note groupings in the other voices in the choir, and also in the accompaniment, and in the solo soprano. Let's look for a 6-note group that has no repeated notes from the original 6 notes in the choir soprano. We find that in the solo soprano. So it appears that we've found the row, 6 notes in the choir soprano, 6 notes in the solo soprano. I'm going to keep track of the various appearances of the row by making a chart. Every time I find one, I'll jot down the transformation of the row. This time it's a prime form, meaning that it isn't transformed, and it starts 0 pitches above the starting note. It's a prime 0, or simply P0. If I search for other appearances of the original row P0, I find one at the end of the second screen. I'm not sure how this fits in with the overall plan of the piece, but I'll add it to our chart anyway. Next, I'll search for other possible transpositions of the row. I look for P1, the row transposed up a half step. No hits. I search for P2 up 2 half steps, and there's a hit, below the original row in the alto voice. The last 6 notes of this row are found in the accompaniment. Let me search for other transpositions. I find one a perfect fourth above the original in the tenor. That's up 5 half steps, P5. And one a tritone above the original in the bass. That's P6. There's a hit on P8 later on in the alto. And a hit on P11 later on in the tenor. We see in our chart that we have 4 voices, each with a different transposition of the prime row. This gives us a consistent dissonant harmony throughout this section. That harmony has intervals, starting from the 0 pitch, a major second, a perfect fourth, and a tritone. This kind of consistent dissonant harmony is exactly the kind of harmony I described in the video on harmonizing atonal music. I've searched for all the transpositions of the prime form of the row, and I've found all the rows on the first 2 systems, but none on the last 2. So let's try to search for all the possible transpositions of the inverted row, the row upside down. Nothing. So how about the row backwards, retrograde? Nothing. Let's try inverted and retrograde. There's an I0R. It's an inversion based on the 0 pitch, backwards. Another I0R. Here is an I2R, inverted up 2 half steps and backwards. An I5R, inverted up 5 half steps backwards. Here's 2 I6Rs. An I8R and an I11R. Let's add all of those to the chart. Take a look at the top voice. It's pretty clear how it's organized. The original row, P0, is followed by P6, the row a tritone up. Since the first and last notes of the row are a tritone apart, P0 ends in the same note that P6 starts on. They share that note, they overlap. The next 2 rows are also a tritone apart, I6R and I0R. They also overlap a note in the middle. There's also an overlap between the second row in that voice, P6, and the third, I6R. P6 ends on the first pitch of the original row, pitch 0, because the first and last notes of the row are a tritone apart. I6R begins on the 0 pitch because it's the inversion starting a tritone above the original pitch backwards. So there's an overlapped pitch between the second row and the third row. Take a look at the rows in the other voices. They share these same relationships with the top voice. They also overlap pitches between each one of their rows. It's all very logical, very neatly done. Using numbers to indicate transpositions makes fairly easy work of this complex example. However, I could have figured it all out without using any numbers. The same can be said of using computers. Virtually anything can be done without using computers, but computers potentially can save a lot of time and effort.